Okay, prepare to have your mind absolutely blown. We all use maps every day, right? But here's the shocker. Imagine trying to find the absolute shortest path across a network with a staggering 64 million intersections. The scale isn't just big, it's truly mind-bending. We're talking about over 10 to the power of 220 possible routes. To brute force test every single one, even if you could crunch a billion routes every second, would demand over 10 to the power of 200 years. That's a number so vast it defies comprehension. This was the impossible challenge, a computational brick wall. Yet, Google and Apple Maps somehow achieve this incredible route calculation in roughly 5 seconds. 5 seconds. How in the world do they do that? It's a scientific miracle, rooted in a stunning evolution of advanced algorithms. The question isn't if it's possible, but how. This computational magic happens right in our pockets. Our journey into this marvel begins way back in 1956. Picture this, Dijkstra's algorithm, a brilliant concept conceived for the Armac computer. This wasn't some abstract idea, it was a practical breakthrough. Dijkstra's genius lies in meticulously exploring nodes from a starting point, constantly maintaining the shortest known distance to each node it encounters. It's like a careful explorer, always noting the quickest way back, prioritizing new paths from the points that are currently cheapest to reach. This elegant, iterative process successfully found a shortest route in 1956 for an actual Netherlands map demonstration. A truly foundational step, showing us that even seemingly impossible problems could be tackled with a clever approach. But the world's road networks are vast, and we needed more. While Dijkstra's radiates outward, exploring in all directions, another breakthrough, the sAlgorithm, arrived to supercharge efficiency for real-world navigation. sAlgorithm introduces a truly clever trick, a heuristic. Think of it as an educated guess, like using the straight-line distance directly to your target to prioritize which nodes to explore next. This brilliant foresight significantly reduces the search frontier, cutting it by approximately 10 times compared to Dijkstra's in complex urban environments, like navigating the intricate streets of New York City. But here's a fascinating twist. sAlgorithm isn't always the undisputed champion. For time optimization, rather than just raw distance, its performance can actually degrade against a highly optimized Dijkstra, especially on massive graphs. Why? The heuristic evaluation itself, sometimes involving complex square root computations, adds its own overhead. It's a delicate balance. And then, another game changer emerged, bidirectional Dijkstra. This isn't just about starting from one end, it's about attacking the problem from both sides simultaneously, searching from your source and your target. This ingenious approach effectively halves the search area by allowing the two search frontiers to meet in the middle, dramatically improving speed. Imagine a journey from Carnegie Hall to Wall Street. This method saw nearly a threefold reduction in the number of explored nodes compared to a traditional unidirectional search. Simply astonishing efficiency. Yet, even these powerful algorithms faced a fundamental limitation. They struggled to truly grasp the inherent hierarchy of our road networks. Our roads aren't flat, they have main highways, arterial roads, and local streets. This led to a crucial industry innovation in the 1990s, pre-processing roads with class annotations. This allowed for hierarchical searches that naturally prioritize major routes before diving into local ones. This concept evolved into automated graph hierarchy construction through a technique called nested dissection, which ranks nodes based on their importance in splitting the graph. It identifies critical bottlenecks, like the 102 Mississippi River crossings on the North American network, and recursively applies this ranking to smaller graph partitions. To guarantee optimal shortest paths while radically limiting the search, they build lower triangles and add shortcut edges. These shortcuts represent the minimum cost path between higher-ranked nodes, ensuring that paths using only lower-ranked, local nodes are considered only when necessary, and ignored otherwise. It's a perfect dance between reduced search space and guaranteed path optimality. It's truly mind-blowing to witness how these layers upon layers of scientific ingenuity conquer what once seemed utterly, fantastically impossible.